Here are solutions to homework set number 4 for ECE 376. The first problem is to determine how long it takes to count mod 16, mod 17, and so on. One way to do that is experimental. I can write a program where I count mod 16, like this code. I'll count on port C. What that does is when I count, the least significant bit goes even, odd, get a square wave out. So if I can measure this time, I know how long it takes to go through the loop. And actually I'm only toggling every 16th count, so this will be 16 times the time it takes to go through the loop. So to do that, I go to MPLAB, take a program like this. Math.h isn't necessary, that's from last semester when we did a cosine, but let's get rid of that. I'll make port B input just because port C is output. That's the only one that really matters. Everybody's binary. Now count mod 16. When I compile, project build, then download, hit reset, try that again, hit reset, program. The code downloads on my board. And here's what it looks like. So this is counting on port C. Every pin is divided by 2. This one is outside the audio range. So divide by 2. Kind of painful. Divide by 2. I can get it. Divide by 2. And here I'm using the piano tuner app. Tell me the frequency. So it's 2400 hertz. 1222. And so on. The net result is I can measure the frequency. Another way is if you have a frequency meter, you can measure it directly on port C pin 0. And I have that. My multimeter will actually tell me frequency. So it's 19.55 kilohertz. What that tells me is as I go through the square wave, it's 19 kilohertz. So it's 10 million clocks per second divided by 2, because I have 2 toggles per edge, or per cycle, times hertz, gives me 255 clocks per toggle. That's this distance. I've got 16 counts per cycle, so divided by 16 is 15.98. So this takes 16 clocks to execute. So the counting mod 16 is 16-ish. I've also got some lines of assembly for this line of code, some lines of assembly for the while loop. So it's 16 or less. That's counting mod 16. Do the same thing, mod 17. When I change this to mod 17, suddenly the frequency really drops, goes down to 483 hertz. That was from 19 kilohertz, meaning this loop right here is 10 million divided by 2 times hertz, 10,000 clocks per toggle, 17 counts per toggle, so divided by 17, this is 608 clocks. Counting mod 16 is much different than mod 17, and really it's like base 9. If I take the number 1, 2, 3, 4, take that mod 10, that's really easy. I just take the ones digit, throw these out. If I take it mod 9, now suddenly that's hard. I have to divide by 9, take the remainder. It's a different algorithm, and that's what you're seeing here. Divide by, or mod 16 is easy. Divide by 16 is a shift. Divide by 17 is hard. That's actually a divide. And that's why you go from 16 clocks to 608. Part C is how long does it take to floating point multiply? Same procedure. Throw in this code, measure the frequency on port C, pin 0, and I got 161 hertz. That tells me it's 30,000 clocks per loop, this time right here. 255 is what it took just to set up the code, so this line of code right there must be the remainder, 30,000 clocks. Divided by 16, because it's done 16 times, 1915. So that one line of code is 1,915 lines of assembly. If I do a double precision divide, I get exactly the same answer. So apparently for this C compiler, the algorithm for double precision floating point divide is exactly the same as a single precision floating point divide. I didn't know that, but apparently it is. Okay, so that's problem number 1. Problem number 2. I want to write a program that goes beep, play 174 Hz for 50 milliseconds. Now I can calculate how many toggles are 50 milliseconds. Each cycle is 1/174 seconds. So it should be 8.3 cycles to give me 50 milliseconds, or times 2, because there's 2 edges. I have 17.46 edges, and that'll be my for loop. That's where the 17 comes from. If I just toggle 17 times at 50 milliseconds, I'll be right around, or at 174 Hertz, I'll be right around 50 milliseconds. That's this guy. The second number sets the duration. That's this period right here. I don't know what that should be, so I'm just going to guess. Let's guess 1,000. If I try 1,000 and write a test routine, I'm just going to go beep, 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 measure the frequency with my frequency counter. I get 312 Hertz. It's supposed to be 174 Hertz, so apparently the frequency is too high. The period is too low. I need to make the period longer, or my count, counting to 1,000, needs to be bigger, and it should be proportional. So 1,000 counts was 174 Hertz. To make it 312 Hertz, I should count to 1787. And if you try it, you sure enough get 174.8 Hertz. It's supposed to be 174.6, almost dead on. So that's kind of one way you can tune a C program. Just guess, you'll probably be wrong, then do a little bit of math and scale it. So we now have a beep routine. Every time my call goes beep, beep, beep at 174 Hertz. And if I try it, so here's the actual program. The original name beep. I've got my beep routine. At the correct beep routine, 17 toggles at 1788 counts per cycle. And that should be 174 Hertz. Take out that pause so my piano tuner can hear it. And you get the 174 Hertz. Almost dead on. So that's problem number 2. Let's disconnect it. I just have my speaker going through 200 ohms from port C pin 0. Try again. So it goes port C pin 0 through 200 ohms, speaker to ground. Problem number 4. Write a program for a craps game. Now, start with a flowchart. I'm going to initialize the ports, start with my bank at $10, display my bank, roll 2d6, check the sum, 7 or 11, I win, 2, 3, or 12, I lose. Otherwise, the point is the sum. I'll then roll another pair of dice, and then check if the sum is equal to my point value. I win. 7 or 11, I lose. Other, keep going. So that's one flowchart. To write the code, this is kind of where the LCD display is really nice. So this is an example of top-down programming. This is actually a fairly complicated program to write, but if you go step by step, it's not too bad. I'm going to start with just the display routine. I'm going to turn on the LCD display, send out a message that's telling me my dice, point, bank value, and I'm just going to display. So if I do this, project build, download, Here's what it looks like. So that's my die rolls. I just rolled a 4, 5, 35, just random numbers. I'm counting to make sure that I can count. That's my display routine. It really helps to have a way to check your code when you write it. First thing you need to do is get the display routine to work. And my display routine just says I'm going to display the first die on row 1, column 0, second die on row 1, column 2, the point on row 1, column 6, and my bank value on row 1, column 12. Kind of arbitrary. Someplace I can show it. Next step. Let's roll 2 6-sided dice. And I forgot how to do that, so I had to go do a Google search to find out how do you pass 2 parameters to a C routine. And the procedure is I do an AND that says this is a variable that gets changed upon return. My subroutine has a character star. That means it's a variable that's going to get returned. I've got 2 numbers, first die, second die. I'm going to wait until you hit the button. Once I press it, wait until you release it. While it's being held down, count mod 36, really, really fast. When I'm done, the first die is n over 6. The second die is n mod 6. That's like if you have the number 0 to 99. The tens digit is the first number, the ones digit the second number. Let's see if that works. So build, project, build, reset, download. So what it should see is the first die, second die, their sum, and the bank. I just get $1 every time I play. Very generous bank. So nothing's happening. Press, release. There's my first roll. A 6 and a 1 gets a 7. Press release. I rolled a 7. 1 and a 2. 5 and 6. 1 and 4. 1 and 3. Okay, so far so good. Now that that works, let's add a check if I win. If the sum is 7 or 11, I'll increase the bank by 1. That's this section of code. If I roll a 7 or 11, I'll increase the bank by 1. This is the beep routine we had before. Display my 2 die rolls, the bank value, and a 0. Wait a second. Check to see that works. Okay, once that works, I'll now add when I lose. If I roll a 2, 3, or 12, I lose. So I'll beep twice. Display the die rolls, my bank since I lost 1. Wait a second. Once I get that to work, now the hard case. If I didn't win, didn't lose, I have a new value called the point. So if I roll a 5, that's my point value. I'm going to keep on rolling, and if my sum is 7 or 11, I lose. If the sum is my point value, I win. So check that. Keep going until I win or lose, and that's what this flag is. This flag is an indicator saying that when a condition hits, flag goes to 1, and that's when I kick out of the while loop. What that does, let's go compile, download. Again, it's a fairly complicated program, but if you go step by step, top-down programming, you can get an answer in a reasonable amount of time. And the LCD display is really useful. It lets me see what's going on. So if I try it, let's go press, release. I rolled an 8. And 8, I didn't win, I didn't lose, but now 8 is my point value. If I roll an 8 next, I win. If I roll a 7 or 11, I lose. So let's try it. Press, release. I just rolled a 9. Nothing happened. A 5. Nothing happened. 3. Nothing happened. 7. Okay, 7 I just lost. So let's try it again. Next game. Toss the dice. I got a 6. Now 6 is my point value. Toss them again. Got a 6. I won. Bank's up to 10. Toss them again. 8. Nope, I didn't win or lose. That's my new point value. 5. Nothing happens. 6. Nothing happens. 5. Nothing happens. 7, I lose. So that's a craps game with your pickboard. The thing to note about that is if you do top-down programming, it's not too bad, but you really need to use the LCD display. That really helps figure out what's going on with the code. That's kind of where we're starting to cover the LCD. Other thing to note is this code was 4266 bytes, meaning it is 2,133 lines of assembly. I would not want to write this code in assembly. In C, it's not too bad. That's kind of the power in C. With a little bit of work, you can actually write pretty complicated programs in C. Much more complicated, well, be much, much harder in assembly. And that's homework set number something. Number 4 for 376.